Somewhere northeast of Los Angeles, there's a mountain pass that millions of people drive through every year without thinking about it once. Trucks grind up the grade. Freight trains run along the base of it. It is the corridor between the Los Angeles basin and the high desert, and to almost everyone who uses it, it is just a stretch of highway with a name, Cajon Pass. In June of 2026, a team of researchers published work describing that pass using a phrase that should stop anyone living in Southern California mid-sentence. They called it an earthquake gate, not a fault line. A gate, a place where the southern San Andreas and the San Jacinto fault systems approach each other closely enough underground that scientists are now openly asking whether, under the right conditions, a rupture could travel through that junction instead of stopping at it. And the same research modeled how much stress has accumulated on the fault segments feeding into that gate. In their reconstruction, several of those segments have now reached levels comparable to, and in some cases beyond, the conditions that preceded past ruptures. So let me answer the obvious question immediately, before anyone panics and before anyone clicks away. No. Nobody has predicted California's next major earthquake. No date exists. No countdown exists. No scientist anywhere has produced a calendar for this. And anyone telling you otherwise is selling something. But something did change this year. Several things did. California's fault model was rebuilt in 3 dimensions and now describes more than 400 active faults in the southern part of the state alone. State regulators released new preliminary earthquake fault zones in May, and that Cajon Pass research changed the conversation about which parts of the system might participate in a single connected rupture. There's also one specific number buried in that stress study that I want you to sit with, because it is the number that generated most of the alarming headlines, and almost nobody explained what it actually means. I will get to it, and I will translate it into something you can picture. But first we need to talk about why the map itself changed, because that is where most of the confusion starts. When you hear that California's earthquake map has shifted, the natural mental image is that scientists somehow discovered the San Andreas wandering into a new location. That is not what happened. Faults are not migrating around the state from month to month. What changed is our ability to represent their geometry, their branches, their connections, and their behavior beneath the surface. For decades, the earthquake maps most people actually encountered were flat. Lines on a page. Here's the San Andreas. Here's the Hayward. Here's the San Jacinto. Useful but deeply incomplete. Real faults are 3-dimensional structures. They tilt, they curve, they split into strands. They approach each other at depth in ways that a surface line cannot show you. Some surfaces intersect, some terminate, some overlap and pass one another like 2 escalators in the same building. And all of that geometry matters enormously when a rupture is tearing through rock at kilometers per second. The statewide California Earthquake Center's community fault model exists to represent that underground world properly. Its newest statewide version contains 556 fault objects and extends across California. In January 2026, the center described an upgraded earthquake default association service built on that statewide model, incorporating more than 100 newer fault representations in Central and Northern California. The Southern California portion received its own detailed scientific release in March 2026, and that component alone describes more than 400 active faults accommodating motion across the Pacific and North American plate boundary. 400. Now think about how far that sits from the picture in most people's heads. Ask someone outside geology to draw Southern California's earthquake threat, and they will draw one line down the middle of the state. One crack, one villain. California is not sitting beside a crack. It is sitting on top of a network. To build that Southern California update, researchers folded in detailed surface traces, relocated earthquake hypocenters, machine learning-enabled earthquake catalogs, and newer focal mechanism data. The result was not simply a higher resolution picture. The new fault representations came out more segmented and more interconnected than earlier versions. Using their association method, the updated model links roughly 90% of regional magnitude 3 and larger earthquakes to a specific modeled fault, a meaningful improvement over the previous generation. And the authors flagged something specific about that increased interconnectivity. It has direct implications for assessing earthquakes that might rupture multiple distinct faults. That is the sentence that matters. Because earthquakes do not care what we name things. We divide fault systems into segments and give them separate names because it helps us study them, publish about them, and argue about them. Nature has never once been obligated to halt. A rupture because the label on the map changed. California's own forecasting already had to absorb this lesson. The Uniform California Earthquake Rupture Forecast, developed by the USGS, the California Geological Survey, and their collaborators, explicitly built in multi-fault ruptures, because earthquakes in the real world jump between connected structures. That single change altered how scientists model the possible sizes and locations of future California earthquakes. Picture a freeway system. You look at one highway on a map and you naturally imagine a vehicle staying on it. Then you zoom in and find the ramps, the interchanges, the parallel routes, and the connectors nobody drew at the previous zoom level. Suddenly, the question is not how far something can travel on one road. It is whether it can transfer to another. Ruptures are not cars, and faults are not highways, but as a way into the problem, it gets you close. And in Southern California, there's one interchange that has researchers' attention. Which brings us back to the pass. To a driver, Cajun Pass is a climb, a truck stop, and a long descent. To a seismologist, it is the complicated seam where major pieces of the southern San Andreas and the San Jacinto systems come near each other. It is also not a hypothetical location in the history of this fault. In 1857, the Fort Tejon earthquake ruptured hundreds of kilometers of the southern San Andreas in an event researchers generally estimate near magnitude 7.9. Fence lines offset. Trees snapped. The ground opened in places where people were standing close enough to describe it. Researchers generally place the southern end of that 1857 rupture in the region around Cajun Pass and San Bernardino, which means the last time the system produced a genuinely enormous earthquake. That junction is roughly where it stopped. The question the 2026 research asks is what happens if next time it does not? The team behind that work built four-dimensional earthquake cycle simulations, using roughly 1,000 years of paleoseismic rupture history to estimate how stress has evolved through the southern San Andreas system. Paleoseismic history means trenching across the fault, reading the disturbed sediment layers, dating them, and reconstructing when the ground broke before anyone was writing it down. 1,000 years of earthquakes, rebuilt from dirt, then run forward as a model. And here is where we need to be careful, because Earthquake Gate sounds more mystical than it actually is. Picture a rupture traveling along a fault. It is not a crack opening in empty space. Rock on both sides has been storing elastic strain for decades or centuries, because tectonic motion never stops, while friction keeps portions of the fault locked. Eventually, some part of that locked system fails and slips. Once the rupture begins, it propagates. Whether it runs 20 kilometers or 200 or transfers through a complicated junction into a neighboring system depends heavily on geometry and on the stress state of the surrounding rock. Sometimes complexity stops it. A bend can stop it. A step over can stop it. A branch can bleed off enough energy to stop it. Sometimes it gets through. And the distance a rupture manages to cover is not a trivia detail. Longer ruptures generally mean larger earthquakes. That is the whole reason this junction is being studied so intensely. A separate 2026 analysis of past earthquakes on these same systems examined exactly this tension, looking at accumulated shear traction against geometric complexity. Their modeling suggests higher accumulated stress can encourage longer rupture propagation, while branches and stepovers still work against it. High stress matters. But high stress does not delete the physical shape of the fault network. Now, that number I promised you. The Cajun Pass study estimated that by 2025, Coulomb stress in their model had reached roughly 2.8 megapascals on the Mojave South segment, about 1.8 megapascals on the North San Bernardino segment, and around 3.6 megapascals on the San Jacinto Bernardino segment. Megapascals are a unit of pressure, and on their own they mean absolutely nothing to a normal person, which is exactly why headlines could do whatever they wanted with them. So here's your reference point. The air pressure surrounding you right now, at sea level, is about 1/10 of 1 megapascal. A few megapascals of accumulated stress on a locked fault surface is not a small quantity of stored energy, but the raw number is still not the point. The point is the comparison. The researchers measured those modeled values against the characteristic stress ranges that preceded past ruptures in their 1,000-year reconstruction, and they found that present modeled stress on several segments now sits at or above those historical ranges. Read that carefully, because the distinction is everything. The model is not saying an earthquake occurs when a specific number appears. It is saying the estimated stress state today has entered territory comparable to, and in some modeled cases past, the conditions associated with previous failures in their reconstruction. There was a second finding, and it is the reason for the word gate. When the modeled stress difference between the San Jacinto Bernardino segment and the Mojave South segment narrowed, those faults appeared more likely in the modeled history to rupture jointly. When the imbalance was larger, they behaved more separately. Stress conditions, in other words, may influence whether rupture behavior stays partitioned or becomes connected through that junction. And if you're sitting there thinking that this sounds like scientists saying the gate is about to open, this is exactly where we slow down, because that conclusion goes further than the science supports. A fault can be heavily loaded and stay locked for a very long time. A fault can also fail without offering any usable short-term warning at all. Stress models can describe the physical condition of a system and identify which rupture scenarios deserve serious planning attention. They cannot convert a stress value into a date. Not Tuesday, not next year. not any year. The USGS is unusually direct about this. Neither the USGS nor anyone else can currently predict a major earthquake by supplying the three things a real prediction requires: time, location, and magnitude. Scientists can estimate probabilities. They can build hazard models. They can update short-term forecasts after a significant event. They cannot tell you the date. That is the answer nobody enjoys, because uncertainty is genuinely uncomfortable. We want a countdown. Earthquake science gives us risk instead. Those are different products. So is the big one getting closer? In the literal sense, yes, trivially. Every day is one day nearer to whatever happens next. Tectonic motion continues. Stress keeps evolving. Major California faults will produce major earthquakes again. But if you mean, has this new map revealed that the big one is 6 months out, or 2 years out, or that anyone has found a hidden clock? The answer is no. The map is becoming clearer. The calendar is not. That may be the most important sentence in this entire video, and it applies to everything that follows. Because the real significance of these models is not that they tell scientists when. It is that they tell scientists how complicated the eventual rupture could be. If you have made it this far, you are the kind of person who wants the actual science instead of the thumbnail version, so do me a favor. Drop your city in the comments. Los Angeles, San Bernardino, Riverside, San Diego, Sacramento, the Bay Area, anywhere in the state. And if you have personally felt an earthquake, tell me the strongest one you remember and what it actually felt like where you were standing, not what you saw on television. Now, there's a second reason the title of this video is literally true, and it has nothing to do with research papers. California updated real regulatory earthquake zones this year. On May 21st, 2026, the California Geological Survey released new preliminary Alquist-Priolo earthquake fault zones for public review, covering the Hayward and Concord fault systems. The affected jurisdictions include Berkeley, Concord, Fremont, Hayward, Oakland, Richmond, San Leandro, Union City, and Walnut Creek, among others, across Alameda, Contra Costa, and Santa Clara counties. On the same date, the survey also released preliminary seismic hazard zone reports affecting additional communities. And before anyone in Oakland hears that and assumes the state just announced something is coming, no, that is not what these zones are. An Alquist-Priolo zone is a regulatory instrument. It identifies areas around traces of active faults with potential for future surface rupture, and it triggers a requirement for geological investigation in certain development situations. Seismic hazard zones cover different dangers, primarily liquefaction and earthquake-induced landsliding. These maps say where specific hazards must be accounted for before somebody builds. They do not say when. They are California attempting to convert geology into decisions made in advance, while there is still time to make them cheaply. Which brings us to the largest misconception in this entire subject. People discuss the big one as though California has a single enormous earthquake sitting underneath it like a bomb with one fuse. Locate the fuse, watch the fuse, warn everyone about the fuse. Reality is far messier. California has many active faults capable of producing damaging earthquakes. The southern San Andreas gets the attention for obvious reasons, but Northern California carries its own serious systems, including the Hayward and Concord faults now involved in those 2026 zoning updates. And some of the most destructive California earthquakes in living memory did not come from the famous fault at all. Northridge in 1994 was a magnitude 6.7 on a buried thrust fault that had not even been the headline threat, and it produced tens of billions of dollars in damage and dozens of deaths in a single dark minute. That is the point about networks. The fault that hurts you is not required to be the fault you are watching. So when people ask whether the big one will hit Los Angeles, even the question hides the complexity. Which fault? Which segment? What magnitude? Which direction does the rupture travel? How deep? What is the ground made of underneath that particular neighborhood? What year were those buildings constructed? What is the condition of the infrastructure serving them? Two neighborhoods can experience the same regional earthquake in completely different ways, and this is where the ground beneath a city becomes almost as important as the fault beneath the region. Seismic waves do not move through every material identically. Thick sedimentary basins can amplify and prolong shaking in ways hard rock does not. Loose, saturated soils can lose strength and behave like liquid, which is what liquefaction actually means when you strip the jargon out of it. Hillside geology governs landslide susceptibility. Distance from the rupture matters. Building design matters enormously. A fault map tells you something crucial. It does not tell you what happens to your street. That is precisely why California maintains several different kinds of earthquake maps that answer different questions. Fault maps, shaking hazard maps, liquefaction zones, landslide zones, three-dimensional structural models, rupture forecasts. When any one of them improves, the state's understanding of its own risk changes, even though not a single tectonic plate changed direction that morning. Now, There is a question that surfaces every time a story like this circulates. Someone checks the recent earthquake list and sees that California has been having small ones, a magnitude 4, then another, then a cluster of smaller events. And within a day, somewhere online, a post appears announcing that the San Andreas is waking up. This is where earthquake coverage most reliably goes wrong. Small earthquakes occur constantly in seismically active regions. Swarms happen, moderate earthquakes happen. Scientists do sometimes update short-term probabilities after a notable event, because aftershocks and triggered seismicity are real phenomena. But you cannot look at a cluster of small earthquakes and conclude they are foreshocks to something enormous. The word foreshock is retrospective. You find out an earthquake was a foreshock only after a larger one follows it. Until then, it was just an earthquake. The USGS notes that supposed precursors, including small swarms and moderate earthquakes assumed to be building towards something, frequently occur without any major event following. That is a significant part of why reliable short-term prediction remains out of reach. So if someone tells you there were 5 small earthquakes this week and therefore California has 7 days left, that is not science, that is content. If someone tells you a fault system is under long-term tectonic loading, that scientists have substantially improved its model geometry, and that a damaging earthquake remains a serious hazard. Communities should be preparing for right now, that is much closer to the actual picture, less dramatic, considerably more useful. Because there is a real danger in treating earthquake preparation as something you begin after an official announcement. There may never be an announcement. That is the entire problem. Earthquake early warning does exist, but early warning and prediction are completely different things. The confusion between them costs people real preparation time. California's earthquake warning system uses shake alert data from seismic sensors to detect an earthquake after the rupture has already begun, then push warnings ahead of the damaging shaking to areas that have not felt it yet. Depending on the event and your distance from it, that can mean a few seconds, or in some cases tens of seconds. Warnings reach people through tools, including the MyShake app and other alert channels. Seconds sound worthless. They are not. Consider what 10 seconds buys when the alternative is 0. 10 seconds to move away from a window, to get under a solid desk instead of standing in a doorway, which is outdated advice in most modern buildings, to protect your head and neck before anything falls. For automated systems, to slow a train, close a valve, or hold an elevator at the nearest floor, for a surgeon to lift their hands. But Shake Alert cannot message you on Monday about Friday. The rupture has already started. The alert is simply racing the seismic waves and winning by a margin measured in heartbeats. Prediction would arrive before the earthquake began. We do not have that. And that gap is exactly where the new fault models live. Scientists are improving everything surrounding the unknown date, the geometry, the catalogs, the links between recorded earthquakes and mapped structures, the simulations, the understanding of how ruptures propagate and where they tend to stall, the hazard zones, the warning network, the date stays hidden. Which sounds frustrating until you consider what these tools actually enable. You do not need the date to retrofit a building. You do not need it to reinforce a water main, or harden a hospital, or plan an alternate route for emergency vehicles, or strap a water heater to a wall stud, or decide what your family does when a phone alarm goes off and everyone is in a different building. Preparation is valuable precisely because the date is unknown. If we knew the date, preparation would be a scheduling problem. Because we do not, it is a standing one. Now think about Cajun Pass again, and what that research is actually good for. If there is evidence that the stress relationship between neighboring segments influences whether a rupture stays contained or continues through a junction, then hazard modelers and emergency planners need that scenario on the table, not because anyone knows it will happen next, they do not, but because a connected, longer rupture produces a fundamentally different shaking footprint than one confined to a shorter section. That is the job of hazard science. Ask what is physically plausible before it happens, then prepare for it. The alternative is discovering after the fact which scenario nobody bothered to model, and Southern California gives researchers plenty of reason to care about rupture length because of what sits above the network. Metropolitan regions, freight corridors, aqueducts crossing the fault, transmission lines, hospitals, fiber routes, fuel pipelines. A major earthquake does not need to flatten a city to devastate it. Break enough water mains, damage enough overpasses, interrupt enough power, start enough simultaneous fires, and block enough routes at the same moment, and the consequences begin feeding each other. Cascade is the word researchers use, and it is the right one. Modern cities are systems assembled out of other systems. Electricity supports communications. Communications support emergency coordination. Transportation moves medical supplies and repair crews. Water supports firefighting, which is often the difference between a damaged neighborhood and a lost one. Hospitals depend on power, on staff who can physically reach them, and on supply chains that assume the roads work. A major earthquake tests all of it simultaneously, which is why the most useful question is rarely whether a city gets destroyed. That question is cinematic and unanswerable. The useful question is which systems keep functioning after the shaking stops. California is not defenseless here, and it is worth saying that plainly. Modern building standards, mandatory retrofit ordinances in several cities, a dense seismic monitoring network, shake alert, and decades of accumulated research all represent real protection. The fact that scientists can now model hundreds of fault surfaces in 3 dimensions is itself evidence of how far this has come. The fact that regulators keep revising hazard zones means the map is a working document rather than a museum piece. But preparedness is uneven, and earthquakes find the unevenness immediately. Buildings are different ages, cities have different budgets. Infrastructure was installed under standards from decades that no longer exist. Households prepare very differently, or not at all. So here's the part you actually control. Enable earthquake alerts on your phone, and in California that includes MyShake alongside standard emergency alerting. Know the response before you need it, which is drop, cover, and hold on, not running for a doorway and not sprinting outside through falling glass. Have a plan for how your household reconnects when everyone is scattered and the cell network is saturated, because it will be. Keep supplies that reflect your actual household, including medications, which is the one item nobody can improvise. Strap the tall furniture. Secure the water heater. Know where your gas shutoff is and what tool it needs. None of this is dramatic. That is exactly why people postpone it indefinitely. Buying water is not dramatic. Bolting a bookshelf to a wall is not dramatic. Practicing what you do when an alert sounds is not dramatic. Neither is a city funding another year of pipe replacement. Earthquake resilience is built almost entirely out of boring decisions made while nobody is frightened. And every one of those decisions becomes extremely interesting about 4 seconds into the shaking. So let us answer the title one final time. Did California's earthquake map just shift? Yes, in several real senses. The 3-dimensional fault model now extends across the state with hundreds of represented fault surfaces, and the Southern California component received a substantial 2026 update describing more than 400 active faults with significantly greater interconnectivity than earlier versions. Regulators released new preliminary fault and seismic hazard zones in May. And the Cajun Pass modeling changed the conversation about present-day stress and about which parts of the San Andreas and San Jacinto systems might participate in a connected rupture. Is the big one getting closer? The tectonic system is active. Stress accumulates and evolves. The new research indicates high modeled present-day stress on important segments and demonstrates why through-going rupture scenarios deserve serious attention. But no map, no stress model, and no swarm of small earthquakes has produced a working clock. The USGS still cannot give you the date, the exact location, and the magnitude in advance. There is no scientific basis for telling anyone this happens next week, next month, or this year, and anyone offering that certainty is offering something the field cannot currently produce. Uncertainty, though, is not the same thing as safety. That is the other half of the mistake, and it is the more expensive half. If a doctor cannot tell you the exact day something will happen, the risk did not disappear. If an engineer cannot name the hour a bridge sees its heaviest load, they do not design it for a calm afternoon. And if seismologists cannot hand California a date, it does not follow that we know nothing. We know where a great many dangerous faults are. We understand their geometry far better than the previous generation did. We know which areas face surface rupture, liquefaction, and landslide hazards. We know multi-fault ruptures happen. We know junctions like Cajun Pass matter. We know several modeled segments are carrying substantial accumulated stress. And we know damaging earthquakes will occur again. The only unknown is when, which may be the actual story here. For more than a century, every generation has looked underneath this state with better instruments than the one before it. First, the fault was simply something people could see where the ground had torn. Then geologists walked and mapped its surface trace. Then seismometers recorded what moved around it. Then satellites measured the ground deforming from orbit. Then computers began modeling the stress. Now researchers can explore hundreds of fault surfaces in 3 dimensions and simulate 1,000 years of earthquakes to estimate the forces acting on them today. The danger did not appear because the map improved. The map improved because we finally got better at seeing the danger that was already there. That difference is worth holding on to. California cannot stop 2 tectonic plates from moving. It cannot negotiate with friction. It cannot instruct the San Andreas to stay locked, and its scientists cannot put the next rupture on a calendar. But human beings control nearly everything that happens before that unknown date arrives. What gets reinforced, what gets replaced, what gets mapped, what gets practiced, what gets funded, what gets ignored, what people understand, and what they do in the first seconds after an alert. The newest maps are not telling California to panic. They are telling California to pay attention. Because someday, somewhere along this network, A line that has sat quietly beneath the landscape for centuries will stop being a line on a screen. It will move. And when it does, the question will not be whether anyone predicted the date. It will be what we did with everything they told us beforehand. We will keep following the San Andreas and San Jacinto research, the fault model updates, and any significant California earthquake sequences. If new evidence genuinely changes what we know, we will break down exactly what changed without converting probability into prophecy. Subscribe if you want those updates when they come. Because underneath all the models and stress calculations and simulations, the reason this science exists at all is simple. People live here, millions of them, and the better we understand the ground beneath them, the better the odds when it finally moves.